Welcome to Lecture 6, Moment of a Force Scalar. In this lecture, I'll be discussing moments in scalar form. Let's consider a force F being applied to a wrench as shown in order to loosen a bolt. The tendency of F, the force F, to make the bolt rotate about the z-axis, and the z-axis is passing through the point O here. The tendency of F to make the bolt rotate is known as the moment of F about O, and is also known as a torque. The distance d here is known as the moment arm, and notice that there's a right angle here. It's a little hard to see, but they've drawn it in on top of the glove there. And the moment arm d is the perpendicular distance from the line of action of the force to the point O. Moments are vector quantities. They have both magnitude and direction. Let's look at the diagram here. We have a force F acting at a perpendicular distance d from the point O. The magnitude of the moment of F about point O, written m sub O, equals the magnitude of F times the perpendicular distance d. And remember, it has to be the perpendicular distance when we're working in scalar between point O and the line of action of F. The units for moments, F times d is force times distance. So in SI will be in Newton meters, and in FPS will be in pound feet. Now for the direction of a moment, the moment axis is going to be perpendicular to the plane that contains the force F and the point O, and it's going to go through point O. So it's going to go, the axis is going to be perpendicular to the plane and through point O. So you can see the right angle indication there. I won't try to draw that again. And the sense of m sub O, the moment on that axis, can be determined by the right-hand rule, where notice here that the force F is trying to rotate about the point O in a counterclockwise fashion, or if you use your right hand and take curl your fingers in the direction that F is trying to rotate about point O, and look at where your thumb goes, you'll see that it points up, and therefore we would draw the moment vector upwards along the moment axis. If F was going in the other direction, it's going to tend to rotate clockwise about point O. And again, if you use your right hand and curl your fingers in the direction of that rotation, you'll see that your thumb points down, and therefore we would draw the moment vector going down the moment axis. Okay, looking at it from a 2D perspective, the vector m sub O the moment vector is coming straight up out of the page, so we don't see it, shown as a regular vector that has some length. It's coming directly out of the page at us, off the screen, out of the screen at us. And we would show its direction by a counterclockwise arrow. If F was acting the other way, we would show M sub O and a clockwise arrow. Similar to a resultant force, we have what's known as a resultant moment, which we write as the resultant moment about O. And that is equal to the sum of the moments about O, which is equal to the sum of the forces times their respective distance from point O. So let's look at the figure here. We have three forces creating moments about point O. And the first thing we need to do to find the resultant moment is to set up a sign convention. We need to be able to deal with, or be able to keep track of, positive moments and negative moments, as they tend to cancel each other out. And we're going to assume that positive moments are counterclockwise, which means that negative moments will be clockwise. And we document that assumption when we write a scalar moment equation by showing that a counterclockwise rotation is going to be considered as a positive moment. Okay, let's look at the three moments in the figure that we're going to sum to create the resultant moment. So the first moment, caused by force F1, is going to be equal to the magnitude of F1 times the perpendicular distance from F1 to point O. F1 tends to rotate counterclockwise about O, so it's positive. F2 creates a moment of magnitude F2 times its perpendicular distance from O, D2, and it's tending to rotate in a clockwise fashion about point O, so it gets a negative sign. And F3, its moment about O is the magnitude of F3 times its perpendicular distance from point O, and it's tending to cause a counterclockwise rotation, so it gets a positive sign. And this equation is going to be the main equation that we use in our scalar moment type problems.